Hey, and welcome Year 10 students. I would love to be with you today, but the government's decision regarding vaccine mandates for all teachers means that it is actually illegal for me to be on the school site, a school that I've worked for 10 years. It's amazing how much power the government thinks that it has and is willing to use to crush people who have a different opinion. Not really happy about that. I would far rather be with you today. But I am praying that God will turn back this unjust law, and that God will frustrate the plans of this government, and that I will be able to return and teach you properly face to face. So in the meantime, I'll be teaching online. You are most welcome to ask for extra tutorials after school. You are welcome to pop around. Just obviously let me know via email if you're struggling with something and need an extra tutorial. If you're worried about that kind of thing, I'm totally happy to do online tutorials via Zoom as well. I am here for you, and I'll do my utmost to support you in your math learning at this time. And even if you're just worried about what's going on, I'm totally happy to chat about that too. So, that said, let's get on to area of similar shapes. So, I want you to think, first of all, let's say we've got a line here, and it's, say, 2 squares long from here to here. And I want to, let's say I want to enlarge the line by 2 times. So what I would do is I'd take that line and I would double the length. So 2 times 2, it's going to now be 4 squares long. And it would be that long. Okay, so that would be my enlargement by 4. So when you've got an enlargement of a scale factor for length, it's really easy. You'll have something like, in this case, 1 to 2. Okay, so the 1 represents the smaller line, and we double it to get the large line. So that's our scale factor of enlargement. Now, things can get a little bit more tricky, or things do get more tricky when we move to area. Let me see, I'll just see if I can. There we go. What we have here is a 2 by 3 shape. Now, if I was to enlarge this by a scale factor of 1 to 2, so, oh dear, I've lost my G. There we go. Okay, we've got length 1 to 2. Now let's apply that to this particular rectangle. Okay, so now instead of 3 along, it's going to be 6 along. So I've extended that by 2, but I also have to do that to the other dimension, which is the width, or the height dimension, I guess. So instead of 2, it's now going to be 4. So that's what I do to the lengths. I double them. So now we've got a 4 by 6. But the interesting thing that happens here, if you look at the area of the original, it's 3 by 2, so you've got 6 squares. And now, in the enlarged version, it's not that you have 12 squares, you see that you actually have 24. So the ratio of the areas is not 1 to 2, but it's 1 squared to 2 squared. In this case, 1 to 4. And this is very important when we come to working out the areas of similar shapes, as we're going to find out today. So let's take a look at this first one here. You see that we've got an unknown length, and we know the length of the smaller shape, and we know that we know the areas of both of the shapes. So what I like to do first with something like this is I'm going to just do my ratios, something to something for length. My smaller length is 3. Now I'm going to look at my areas. And the area that I have for the small one is 7 to 28. Now I would simplify that by dividing both of those by 7. And now I can write those as squareds. 1 is 1 squared. And if I square root 4, I get 2 squared. Which means that the ratio of my length should be 1 to 2. Right, because area is 2 dimensions, so I would just get rid of these squares, and to get my 1 dimension I have 1 to 2. So if I've got an area, a length of 3, I must be timesing by 3 this ratio, which means if I times this by 3, don't know why it's doing it. Oh, I see, it's into shape. I times that by 3, so I should have a length of 6. So I think in the first case, x is equal to 6 centimeters. Now let's take a look at this next one. In this next one, again, we have an unknown length, but we know the length of the smaller one. So we could go length. We're going to have 2 to the larger one, which I don't know at this point. I'm going to go down here and get my area sorted out, because that's what I do know. I've got 1.6 to 3.6. Now I'm going to divide both of those by 1.6, so I'm going to get 1, 2. Now when I chuck this on my calculator, what is 3.6 divided by 1.6 is giving me 9/4. Now another way of writing that, I'm going to take this, I can write that as 1 squared to 3 over 2 squared. Now if you don't know how to get the 3 over 2, all you need to do is type square root of 9 over 4 on your calculator and it will give you 3 over 2. Which means that the ratio, so I can now use this, that means that my ratio of lengths is 1 to 3 over 2. Now how do I get from 1 to 2? I multiply by 2. How do I get from there to x? I multiply by 2. So that'll be 3 over 2, which is 1.5 times 2. So therefore x is 6 over 2, which is equal to 3. Now you might be wondering where this square business comes from. Okay, I kind of explained it at the beginning, but let me just go back to that. Let's take this example here. We've got 2 going to 4, so how do we what are we timesing by? We're timesing by 2. And we've got 3 going to 6, so we're timesing by 2. So the ratio is 1 to 2, but we're doing it, to get the area, we're doing it 2 times. So that's why we've got 1 squared to 2 squared, because we're multiplying by 2 twice to get the area. This is twice the 2, and this is twice the 3. So ultimately we're timesing by 4 to get the area of the bigger shape. Okay, moving right along. Let's see, what have we got here? Okay, this time, we still don't know the length. Okay, still don't know the length. Now, what we'll do is we'll set up the same scenario again. So with the lengths, I've got my smaller one is 1.8 to something. And then I've got my area. And for my area, I've got 4 to 12, which we can simplify as 1 to 3. And another way of writing that is 1 squared to square root 3 squared. Okay, because I've just taken the square root of 3, which is square root of 3, and squaring that gives us 3. So this is the ratio of areas, which means that the ratio of lengths must be 1 to square root 3. And therefore, to find x, we're just going to times the square root 3 by 1.8. So x is going to be 1.8 times square root 3, which, if we chuck that on the calculator, what does that give us? To 3 significant figures is 3.18. Now the next one's a little bit different because this time you can see that the unknown is actually an area. So let's look at our lengths first. This time we've got the small one is 6 to 8. So I'm just going to divide both by 6. So I get 1. Now when I divide 8 by 6, I get 4/3. Right, 8 over 6 is the same as 4 over 3. Now the ratio of my areas, therefore, is going to be 1 squared to 4 over 3 squared, because we're now in 2 dimensions, which is the same as 1 to 16/9. Now we know that the area of the small one is 16. So to get the area of the large one, I'm going to times by 16. And this gives me 256 over 9, or if I want to write it to 3 significant figures, I would write it as 28.4. And it's recurring in this particular case. Okay, allow me to do perhaps one more of those. Let's see, yeah, not that one. Perhaps we'll take another one where we don't know the area. Yes, this one here looks quite good. Leaves you one fewer to do. I'm sure you're very upset about that. Okay, so looking at this one here, we're going to write down the ratio of lengths. So we've got the smaller one is 5 and the larger one is 8. I'm going to divide both of them by 5 to get into a 1 to something ratio. So my length ratio is 1 to 8 over 5. And therefore my area ratio is going to be 1 squared, which is just 1, to 8 over 5, all squared, which is 1 to, what's that, 864 over 25. Okay, now we know that the area of the small one is 22, so we're going from 1 to 22, which is times by 22. And we must do the same now that we're in area to the larger one. So we're going to times the 64 over 25 by 22. Now what does this give us? 64 over 25 multiplied by 22. I'm getting 56.32. Or 56 point... I'll just do 56.32. Alright, now the last type, this is the next exercise that I wanted you to work from, is similar shapes. Again, just a bit more complicated. So you can see, I hope, that CED is actually similar to CAB. Now, that means that the ratio of CA, so we'll look at length, CA, that's this bit here, is 1, 2, now CE is 1, and then CA is 4 plus x. Now that ratio, so that the ratio is 1 to 4 plus x. Now let's look at the ratio of areas. We've got the small one is 10. The large triangle is actually 90, if you think about it. So we've got a 1 to 9. Why is it 90? 10 plus 80, because the big triangle includes that green bit as well. Definitely not to scale, as you can see. Now we can do the areas as 1 squared to 3 squared. And that means that the ratio of lengths is 1 to 3. Sorry, I just messed up my length at the beginning. It should be 4 to 4 plus x. I hope that didn't confuse people too much. Now, what am I doing here? I'm timesing by 4. And to get to this ratio, I must times by 4. So that tells us that 12 is equal to 4 plus x, which means that x should be equal to 8 centimeters. Well, I hope this gives you somewhat of an idea about how to do these. If you're getting stuck, you're most welcome, if the supervising teacher is satisfied with this, to chat quietly, whisper to the person next to you to get some help if you're stuck. Obviously, you've got your answer book that you can take a look at to see if you're going okay. And of course, I've sent you a message on ThinkWave with my email address if you're getting stuck, and I'm most happy to help you there as well, and even offer tutorial online or whatever after school. So keep in touch, let me know how you're going. Take care. God bless you.